So basically, there are three equations which you will be using to solve problems in thermodynamics. Okay. The first is the first law of thermodynamics. Delta Q, the heat supplied to a system. Okay. Some of it gets stored as internal energy within the system, and the rest of it gets converted to work. Delta Q is equal to delta U plus delta W. Fine. The next equation is the equation of state for an ideal gas. PV is equal to nRT. Every ideal gas must or will obey this equation. And the third equation, whatever we derived yesterday, is for internal energy, U. The total internal energy of a gas, ideal gas, can be calculated as F by 2 nRT. And because PV is equal to nRT, you can write internal energy as F by 2 multiplied with PV also. If you know the pressure and volume, that way also you can calculate the total internal energy of a gas. Okay. Let's solve some basic problems based on these equations, and then we will get into thermodynamic processes. Okay. First question. Right. So consider this. When 200 joules of heat is supplied to 4 moles of a monoatomic gas initially at 27 degrees C, it is found that 10% of the heat is converted to work. Okay. Somehow through some process, 10% of the heat is getting converted to work. Fine. Based on this, calculate the change in internal energy of the gas and see. You know the formula for internal energy, F by 2 nRT. Okay. U is equal to F by 2 nRT. F is the number of degrees of freedom. It depends on the type of gas. So during a certain process, since the gas is already monoatomic, if it continues to remain monoatomic, degrees of freedom will not change. Okay. And you assume that number of moles is also not changing. We are not introducing extra gas. We are not allowing the existing gas to escape also. So F and N remain constant. Then temperature is the only thing that will change if internal energy changes. Okay. So based on how much is the change in internal energy, you should be able to tell how much is the change in temperature of the gas, and you should also be able to tell what is the final temperature of the gas. Okay. Try this, all of you. Read the question carefully and find out these three terms, these three quantities. And just for convenience, in this particular problem, take R to be approximately 8 joule per kg, sorry, joule per mole per Kelvin. Okay, it's actually 8.314, but let's approximate it to 8. Okay, any answers, anyone? At least change in internal energy. See what happens when you supply heat to a system. Some of it gets stored as internal energy, the rest of it gets converted to work. Okay. Fine. You're asking for some time to solve. Okay, solve it quickly. Okay, let's discuss the answers. See, it is given to you that 200 joules is supplied. Okay, I got one answer for the first part as 180 joules. That is correct. Out of 200 joules, 10% of the heat is converted to work. 10% of 200 is 20 joules. So work done here is 20 joules. We supply 200 joules of heat. We know from the first law of thermodynamics, or basically from energy conservation, that delta Q, the heat supplied, is equal to the sum of change in internal energy plus work done by the gas. Okay. So this is 200 joules. This is 20 joules. Then the rest 180 will be delta U. So the change in internal energy of the gas is 180 joules. Okay. Now, due to that 180 joules that it is storing, there will be a certain change in temperature. Okay. How is internal energy related to temperature? We know U is equal to F by 2 N R T. Okay. Now, if internal energy changes, see, degrees of freedom is not going to change. The gas remains monatomic. Okay, so degrees of freedom won't change, number of moles won't change. I told you this already. So the only thing that can change is temperature. So you can write it this way. Initial internal energy is F by 2 nr initial temperature. Okay. And final internal energy is F by 2 nr final temperature. And then you subtract these two. Final internal energy minus initial internal energy becomes F by 2 nr. Those terms are not changing, multiplied with final temperature minus initial temperature. Therefore, change in internal energy delta U is F by 2 nr delta T. Okay, this is how we are going to make use of that internal energy formula while solving problems in thermodynamics. Usually in the questions that will be given to you, there won't be any change in the number of moles or the type of gas. See if it changes, suppose extra number of moles are introduced, or sometimes monoatomic may fuse and become diatomic, or diatomic may disintegrate to become monatomic. So the degrees of freedom can change. Then you will have to write it this way. Initial, final, you write separately and subtract. Okay. But suppose degrees of freedom, number of moles are not changing, then you can use it like this. Delta U is equal to F by 2 nr delta T. Now in this question, out of the 200 joules supplied, 10%, that is 20 joules was converted to work. So 180 joules was stored as internal energy. So we can write 180 joules is equal to, see, it's a monoatomic gas. It has 3 degrees of freedom. So 3 by 2. How many moles were there? 4 moles were there. And I asked you to take R as 8 multiplied with delta T. That's all. You will get the temperature change from there. Not a big deal. 2 times 3 and 180 will go 60 times. So the change in temperature will be 60 divided by 2 8 is 16. Okay, you can simplify that. Anyway, you get the change in temperature and you were told that the initial temperature is 27 degrees C. Fine. Now, if initial temperature is 27 degrees C and you know the change in temperature, okay, 60 by 16, this is 4 times 15, 4 times 4, that becomes 3.75. This will be in Kelvin, but you know that changes in temperature on the Kelvin scale are same as changes in temperature on the Celsius scale. So delta T is 3.75 Kelvin. So the final temperature would be 27 plus 3.75, that is 30.75 degrees C. You can write it as 3.75 degrees C also. Change in temperature is same on Celsius scale and Kelvin scale. Okay. So basic application of first law of thermodynamics and the formula for internal energy. That is what you learned from this problem. Okay. Hope this is clear to all of you. If you have any questions, you can ask. Right. Now, according to the first law of thermodynamics, delta Q is delta U plus delta W. Okay. We have a proper formula for internal energy of a gas, F by 2 nRT. Change in internal energy will be change in that term, F by 2 nRT. Okay. Now, as I said, the main thing we learn in thermodynamics is how to convert heat to work and how much heat can be converted to how much work. Okay, so you need to know how to express work done by a gas. Okay, can one of you tell me from what you learned in mechanics, what is the basic formula for work? By definition, what is the basic formula for work? W is equal to, you all must answer such questions. These are very simple definitions. Now, without those, like what is the, I mean, how will you learn how to find out work done by a gas? Try to recollect and tell one of you. What is the basic formula for work? Okay. Generally, work done is integral F dot ds. Okay, integral force dot displacement. Fine. Now assume there is a gas present in this space. Now, as we know, when gas molecules are at a temperature more than 0 Kelvin, they will be moving around randomly. And if they are moving around randomly, they will exert pressure on the walls of the container. So, due to the random motion of gas molecules, there will be forces acting on the walls of the container. Always. At any temperature more than 0 Kelvin, there will be a force acting on the wall of the container if there is gas present. Okay, so you can imagine forces acting like this everywhere. Here also. Okay. Let's assume this piston that is present is movable. If the piston undergoes some displacement, okay, let's say it moves to this position. See, this is a simple case that we are considering, simple container that we are considering, okay, in which gas is enclosed with a piston. Let's say the piston undergoes a displacement dx. Now, it's not necessary that every time gas will be stored in this kind of container only. Okay, the expansion could happen everywhere, not just on one side. Okay, so the walls of the container could move. I mean, every wall of a container could move, right? But the result that we are going to derive is generally applicable, not just in this case. Okay, so suppose there is a piston of cross-sectional area A. Fine. So A is the area with which the gas molecules are in contact. Now assume the piston undergoes a displacement dx. Now because of the pressure of the gas, let's say the gas is at a pressure P. Because of the pressure of the gas, the piston will be experiencing a force. How much force? How do you calculate force resulting from pressure? Pressure multiplied with area. That is the force acting on the piston. And let's assume the piston undergoes an outward displacement dx. So if there is a force and a displacement, there will be work done. Therefore, during that displacement, the small amount of work done by the gas will be F dot ds. The force here is pressure multiplied with area, and the displacement here is dx, and they are both in the same direction. Okay, so the small amount of work done will be PA dx. Now, P is pressure of the gas at that moment. A is the cross-sectional area of the piston, dx is the displacement it undergoes. Then A multiplied with dx effectively becomes this volume. Area multiplied with the distance moved by the piston becomes equal to volume expanded by the gas. Okay, so you can write work done by the gas in this during this small expansion as P multiplied with small change in volume dV. So in mechanics, to calculate work done, we used to use the formula integral F dot ds because their force will be given directly, or you will know how much force is acting and you will know the displacement. When it comes to thermodynamics, when it comes to work done by a gas, okay, this is how you do it. You write dW, the small amount of work done by a gas, is the pressure of the gas at that moment multiplied with the small change in volume. Okay, now understand this equation carefully. Pressure of a gas can never be negative. Gas molecules cannot pull some surface. They can only push surface because gas molecules will be moving around randomly. They can only exert an outward force on the wall of a container. They can never exert an inward force. So negative pressures don't exist. Okay. So pressure is always a positive term. Fine. Now, if dV is positive, then work done will be positive. If dV is negative, work done will be negative. Okay. What is dV? Small change in volume. When does dV become positive? When volume is increasing. Means when gas expands, dV will be positive. Work done by the gas will be positive. We are deriving expression for work done by a gas. So if a gas expands, fine, work done by the gas will be positive. In that expansion process, pressure may be increasing, pressure may be decreasing, it may remain constant also. But whatever it is, whether pressure is increasing, decreasing, or remaining constant, it will be positive. Fine. Positive value only could increase, positive value could decrease, but it stays positive. So since pressure is always positive, expansion results in positive work done. Compression of a gas results in negative work done. Okay. If the volume of a gas decreases, then it will do negative work. Why? Because, see, gas molecules due to random motion will always be pushing the boundaries outwards. But somehow, if the boundary moves inwards due to external pressure being higher or due to some process, okay, gas molecules will be hitting the container outwards only, walls of the container outwards. But if the walls somehow move inwards, then force is outward, displacement is inward, work done by the gas will become negative. Now, walls of the container moving inwards means what? Volume decreasing. So, if volume of a gas decreases, work done by the gas will be negative. If volume increases, work done will be positive. Okay. So, dW is equal to PdV. And if you want total work done by a gas, you can write delta W is equal to integral of small amounts of work done. That becomes integral P dV. So when it comes to gases, this is how we calculate work done by the gas. Integral P dV. We don't write integral F dot ds. Okay, this is derived from integral F dot ds, but this is how we use it. Okay. So when you supply heat to a gas, some of it gets stored as internal energy, the rest gets converted to work done by the gas. You can also write this equation as dq is equal to du plus dw. Okay, so it depends on the situation. Sometimes you can use it this way, sometimes you will have to use it this way. You'll understand when we solve problems. So what do we know now? We know how to express internal energy, change in internal energy in terms of temperature. U is equal to F by 2 nRT. And we know how to calculate work done by a gas. If you know the pressure volume equation, see, you to integrate P dV, what do you need to know? You need to know pressure as a function of volume. Okay, then you can tell how much is the work done. You write that function there, you substitute limits, you will get the work done. Okay, so we know how to calculate change in internal energy, we know how to calculate work done. And if you know how to calculate these two, delta U and delta W, indirectly you know how to calculate delta Q, right? Okay. Now let's solve some problems, two problems based on this formula. Work done by a gas is integral P dV. Okay, let's just apply this equation. First problem, assume the pressure of a gas varies with volume as P is equal to some constant, let's say K, divided by V. Okay, suppose it is like this, some constant divided by V, and initial volume of the gas is V naught, final volume of the gas is 3 times of V naught. So you know how pressure varies with volume. So you know the pressure volume equation and you know the limits of volume also, from which volume to which volume it is changing. I want you to calculate, like based on this, I want you to calculate how much is the work done by the gas. Okay, you have the formula right here. All you have to do is substitute the pressure equation there and integrate properly and then substitute limits. Do this, all of you, calculate work done by the gas in this process. Right, let us discuss the solution. Now work done is calculated as integral P dV. To perform that integration, you need to know pressure as a function of volume, which is already given to you here. Okay, so directly substitute delta W is equal to integral K by V dV. And limits for volume will be from V naught to 3V naught. Okay. Now K is a constant, you can put it outside the integral. And you will be left with integral 1 by V dV. And integral 1 by V dV is ln V, natural log. Okay. So the integral becomes k times ln v. And in this, we need to substitute limits v naught to 3 v naught. Substitute upper limit, it becomes k times of ln 3 v naught first minus lower limit is v naught. Okay. And basic mathematics, ln a minus ln b is ln of a by b. So this becomes k times ln of 3v naught divided by v naught. So the answer is k ln 3. That is the amount of work done by the gas in this process. Okay. It- Uh, some of you may not have been knowing this integral, but integral 1 by v dv is ln v. Okay. Right. Let's try another problem. Now see, we just proved that work done by a gas can be calculated as integral P dV. Fine. If you know the pressure as a function of volume, you can substitute the function here and integrate. Okay. But sometimes they can give you graphs also. How pressure varies with volume, they can give you in the form of a graph instead of an equation. Okay. Now, how do you integrate from a graph? You basically have to take area under the graph or area between the graph and the x-axis. Now here we are integrating pressure with respect to volume, no? So work done by a gas can be expressed as or can be calculated as area between the PV graph, pressure volume graph, and the volume axis. Okay, what do I mean by this? Just a moment. Consider a graph like this. Now see, pressure of a gas and volume of a gas will never be negative. Okay, they may become zero. Zero is also very difficult. It's difficult to compress a gas to zero volume. So the PV graph, pressure volume graph, will always be in the first quadrant only because none of them can take a negative value. Okay, so suppose you have pressure on the y-axis and volume on the x-axis. And during some process, as heat is supplied to a gas or removed from a gas, let's say the pressure change, like let's say initial pressure is P naught, initial volume is V naught, and as the process goes on, let's say the pressure changes to some final pressure, let's say 4 times of P naught, whatever it is. Okay, you can just write in P initial, P final. You don't have to assign values to them. And V initial to V final. Let's say the volume changes from V initial to V final. Okay, and I have shown an arrow also so that you know how the process or what is happening to the gas as the process is being carried out. Okay, just giving you the graph is not enough. They'll have to give you the direction in which the graph was obtained. Okay, like depending on what you do to the gas, it may be going from this initial state A to the final state B, or depending on what you do to the gas, it may be undergoing the reverse process also. So you need to know what exactly is happening. Why do you need to know what exactly is happening? If the process is carried out from A to B, that means volume is increasing, gas is expanding. If gas is expanding, work done is positive. Okay. If the process is carried out from B to A, that means as heat is supplied or removed from a gas, suppose it undergoes the reverse process, that means the gas is getting compressed. Then work done by the gas will be negative. Okay. Anyway, we just discussed that work can be calculated. Work done by a gas can be calculated by taking the area between the PV graph and the volume axis. Now, what you are shown here is the PV graph. You have to take the area between this graph and the volume axis. So this area is what matters. If volume was on the y-axis, then you would have taken area with y-axis. In this graph, volume is on x-axis, so you'll have to take area with x-axis. Fine. Whatever is the numerical value of this area, that will be the numerical value of work done. But the direction of the process is also important. If the process is carried out in such a way that gas is expanding, then work done will be taken as positive of this area. If the process is carried out in such a way that the gas is compressing, getting compressed, work done will be calculated as negative of this area. Okay. So work done can be calculated by calculating area between the PV graph and the volume axis. But you should know whether you should assign a positive sign to it or a negative sign to it. That depends on whether the gas is expanding or its volume is decreasing. Okay. Let's solve one simple problem based on this graph also. I'll just give you a pressure volume graph. Based on that, you tell me how much work is done by the gas. During some thermodynamic process, as heat is supplied to the gas, let's say something like this is happening. This is how the pressure and volume are varying. Okay. Now, at one point, let's say the volume is V naught, pressure is 2 P naught. Okay. Assume this is the initial state of the gas. And from there, as we supply heat or something, it goes to a final state. Following a linear graph, it goes to a final state where the final volume is, let's say, 4 times of V naught, and the final pressure of the gas, assume it is 3 times of P naught. Okay. So A is one state, B is one state. Suppose the process is carried out from A to B. So from an initial pressure 2 P naught, volume V naught, the gas is going to a final pressure of 3 P naught and volume 4 V naught. So what is happening to the volume? From V naught, it is increasing to 4 V naught. Volume is increasing, gas is expanding. So work done will be positive. So in the process A to B, how much is the work done by the gas? Calculate this, all of you. Answer will be in terms of P naught and V naught. Do this quickly. Right. So you just need to calculate this area, the area between the PV graph and the volume axis. Fine. The shape is a trapezium, but you can split it into a triangle and a rectangle. We'll first calculate the triangle's area. The base here from V naught to 4 V naught, the base becomes 3 V naught. And the height of this triangle 2 P naught to 3 P naught is P naught. Therefore, this area becomes half base into height, 3 V naught multiplied with P naught. Next, the rectangle's area. The length of the rectangle is 3 V naught, the height is 2 P naught. Therefore, this area, the area of the rectangle becomes 3 into 2, 6 times of P naught V naught. Okay, so the total area between the PV graph and the volume axis becomes 3 by 2 plus 6 is like 12 by 2. Add them, it becomes 15 by 2 P naught V naught. Okay, therefore the work done will be, now see, the process is being carried out from A to B, state A to state B. Volume is increasing, therefore work done is positive of this area. So 15 by 2 P naught V naught itself. Had the same process been carried out from B to A, so you will have the same graph, but the arrow will be in reverse direction. So area will come out the same, 15 by 2 P naught V naught. But you should understand that if the process is carried out from B to A, volume is going from 4 V naught to V naught. Volume is decreasing. Therefore, the work done by the gas will become negative. Okay. So in that process, the work done would have been minus 15 by 2 P naught V naught. That is how you make use of the PV graph to express work done by a gas. Okay. Now, suppose you supply a heat delta Q and it results in a temperature change delta T. Now we are talking about gases, no? The like whether you supply heat or remove heat, we'll assume the gas stays as a gas itself. Okay, we don't assume that when you are removing heat, the gas can undergo a change of state. No. Okay. As far as your syllabus is concerned, in thermodynamics, gas remains a gas. Okay. We will discuss some questions where there may be a state change involved, but those are like exceptions. Usual thermodynamic processes, gas remains a gas. Okay. Suppose a heat supply of delta Q results in a temperature change of delta T. Now, in calorimetry, we used to write equation like this. If state change is not happening, delta Q was related to delta T as delta Q is equal to ms delta T, where m is mass of the object and s is the specific heat of the material with which the object is made. You can do the same for gases also. But usually when it comes to gases, they don't specify the mass of the gas. Okay, they specify the number of moles of a gas. So instead of writing it in this form, delta Q is equal to ms delta T, we write the equation in a slightly different form. So when it comes to gases or in thermodynamics, heat and temperature are related as delta Q is equal to Nc delta T. Okay, instead of mass, we use number of moles. Instead of S, that is specific heat, we use C, which is called molar specific heat. Okay, how do you define this? You can say C is equal to delta Q by N delta T. So how can you define this? Delta Q is the heat required, okay? Heat required or the heat that must be supplied. So when will C be equal to delta Q? When N is equal to 1 and delta T is equal to 1. So you can say molar specific heat C is basically the heat required to raise the temperature of 1 mole of a gas by 1 unit. Okay. When number of moles is 1 and temperature change is 1 unit, C becomes equal to delta Q. So C is the heat required to raise temperature of 1 mole of a gas by 1 unit. So the definition is analogous to the definition of mass specific heat S. What is mass specific heat S? It is the heat required to raise the temperature of unit mass by 1 unit temperature change. Okay. So here when it comes to gases, we use something called molar specific heat. That is the heat required to raise the temperature of unit mole, 1 mole by 1 unit. Okay. Uh, Quickly derive the SI unit and dimensional formula of molar specific heat. Right. Any answer for SI unit? Heat will be expressed in joules. And number of moles is in moles itself. Okay. Mole is a fundamental quantity in the SI system, and mole is a fundamental unit also in the SI system. Temperature change will be in Kelvin. You can write it in Celsius degrees also. Therefore, molar specific heat, the SI unit will be joule per mole per Kelvin. You can also write joule per mole per Celsius degree. Since its temperature change, it will be the same whether you express it in kelvins or in Celsius degrees. Okay. And then the dimensional formula, joule energy is ml square T power minus 2 divided by mole is mole itself and temperature is in Kelvin. The dimensional formula is K. Therefore, the dimensional formula for molar specific heat becomes m L square T power minus 2 mole inverse Kelvin inverse. Okay, quite a lengthy formula, but it's easy only. Based on the formula of the quantity, you can express its SI unit and dimensional formula. Okay. So we had solved one question in this class itself where the amount of heat supplied was given to you and you found out temperature change and all. Okay. When 200 joules of heat is supplied to a monatomic gas, 4 moles of a monatomic gas at 27 degrees C, 10% was converted to work. Based on the given information, we could find out the temperature change also, delta T. It resulted in a temperature change of 3.75 Kelvin. Okay. Now, if you know the heat supplied delta Q, that is 200 joules, And delta T, that is 3.75 Kelvin. If you know heat supplied and temperature change, and you know the number of moles also, for how many moles this happened, you can tell the molar specific heat of this gas. Okay, so let us do that in this question itself. Molar specific heat is delta Q divided by N delta T. Now, how much heat was supplied? 200 joules was supplied to how many moles? 4 moles. And what is the resulting temperature change? 3.75 or 60 by 16. I'll write it like this. That's all. That becomes the molar specific heat of this gas. Okay, so in a certain process, if you know how much heat is resulting in how much temperature change, you can tell the molar specific heat. Okay. So the three basic terms that you see in the first law of thermodynamics, delta Q is delta U plus delta W. This is how they are basically related. And delta Q can be written as NC delta T. Delta U can be calculated as F by 2 NR delta T. I'll have to keep a star here because this formula for change in internal energy is valid only if the degrees of freedom and the number of moles do not change. What if they change? You will have to do it this way. Final, okay, final degrees of freedom divided by 2, final number of moles are temperature final. That will be the final internal energy of the gas minus initial number of degrees of freedom divided by 2, initial number of moles are T initial. That will be the initial internal energy of the gas. Final minus initial gives you the change. Okay. So this is general. But as I said, as far as physics is concerned, what we are interested in is supply of heat and conversion of heat to work. We don't change the number of moles or the type of gas during the process. Okay, so so degrees of freedom and number of moles, F and N, are not going to change. So mostly this is how you will calculate internal energy changes. Okay, and then work done. Delta W is integral P dV. Now, how will questions in thermodynamics be asked, or what will you usually have to find out in thermodynamics? They will give you some process, they'll tell you what is happening with a gas, and based on what is given, you will be able to find out two out of these three terms. And if you know any two out of these three, the third one can be calculated because you know delta Q is delta U plus delta W. So if you know two, the third one can be calculated. That is what usually you'll be asked to do. Based on the process, you'll have to calculate two of them. And based on those two, you'll have to calculate the third one and answer whatever it is that they are asking. Okay. So remember, all of thermodynamics, as far as your syllabus is concerned, will be based on these equations only. Delta Q is delta U plus delta W. And each of these terms has a formula. And along with these, you'll be using the equation of state, ideal gas equation, PV is equal to nRT. That's all. Simple application of these equations is what is involved in thermodynamics. So next class, we will discuss thermodynamic processes. Okay. The different ways or the different processes which a gas can undergo as it converts heat to work. Okay. And how to make those processes more efficient. That is what we'll be discussing over the next 2, 3 classes. Okay, but I want you all to revise thoroughly before attending the class. Most of you are not responding at all. Okay, and from tomorrow, I want you all to unmute and respond. Whatever it is that you want to tell, whatever question I ask, you will have to answer immediately. Let's keep the class interactive. Okay, and please join on time. I am again observing that most of you are not joining on time. Whatever time is mentioned, you have to join by then. Okay, thank you all. We'll continue tomorrow. We'll discuss thermodynamic process.